Okay, go ahead.
Thank you. Thanks the organizing committee for this nice conference, and thank you for the invitation. So I will talk about non-local Lasry-Lions type problem. What is this? Let's start with a lot of results by Lasry-Lions. So the equation that Lasry-Lions studied is a Hamilton-Jacobi equation that I want to study a Hamilton-Jacobi equation too, which we replace the Laplacian here by the fractional Laplacian. So it's an equation which is start where you have the fractional Laplacian, a gradient term, and a lambda u time and a forcing term. And let's say with zero boundary condition, that can be extended with other boundary condition, but and P will be a parameter between 0 and 2s, which is the critical scaling somehow of the equation. And we should have, that's why unbounded, not only large. So at the boundary could be plus infinity or minus infinity. And here is the definition, the standard definition of the fractional Laplacian. So that's the object of my talk. I want to start with the result by Lasry-Lions. What they say about this equation when you put the case S equal to 1 or the Laplace equation for that type of problems. So in '89, they prove really the existence or uniqueness of large solution. They studied this problem with N with P in between larger than 1 and less than 2 and a positive lambda. This is relevant here. And let's say continuous nonlinearity. Even f can be unbounded and locally in L infinity, but let's, for simplicity, let's take f a continuous function. So what they prove? They prove that exists a unique solution that behaves like the distance to some power related to p, which is minus p minus 2 over p minus 1. So it's really goes to plus infinity. And here this is the distance to the boundary. So this is the behavior, and this is when p is less than 2, and when p is 2, they found a logarithm profile for the solution. And in this work, I will concentrate here in my talk for p less than 2 or 2s at the end, but in that paper, Lasry-Lions also studied the case p bigger than 2. So, but just I will not consider that in this talk. So, what? They connect this equation, Lasry-Lions in the same work, connect this equation with optimal stochastic differential equation. What they want to do is constrain the Magna motion by controlling the drift, so that the admissible drift is so that the process never exits the domain. So you put a lot of wind, you have a bound motion going around, and you put a lot of wind. So wind, let's say drift, wind, I call it wind because it's more natural to think about wind. You put wind so that the bound motion cannot exit the boundary, near the boundary. So the drift become unbounded. That's near the boundary. So that's, of course, this may be admissible drift do not exist at the beginning, but at the end they prove that they exist and are related to the equation. So it's really stochastic control, and f is the running cost, and lambda represents the discount factor. And why they prove that using the dynamical programming principle, the value function is the unique solution of the equation. And this is, yeah, this value function is obtained by minimizing the running cost. Yeah, this is standard, but in the class of admissible drift, so drift that never exit the domain, and and the cost depend on F, like standard, and a feedback term, depending on P and the drift. A feedback term, so if you put more drift this costs you more cost. So if you put very large wing, you produce a lot of cost. So this is why also the solution became unbounded near the boundary, and the cost function became more or less unbounded near the So that's Lasry-Lions result. They go further, and but yes, they studied the so-called ergodic problem. What's the ergodic problem? Is when you take this problem and study the limit as more or less the coercivity term, which is lambda here, goes to 0. And what they prove in the same paper, they prove that you need to fix a point. So your solution minus a fixed point goes to a solution as lambda goes to 0 of the problem without lambda, but you have some what is called the ergodic constant. You have to plug in a positive constants there. So no, it's not positive, it's the ergodic constant. I say positive because in the positive case something happened, but you find a constant to solve the equation. Notice that this equation has an invariance. If you add a constant, you still have a solution. You can have, so it's without, actually this is a large, they find a large solution, which is the limit of the large solution mentioned before. So it's really that. So maybe I will now connect this with the parabolic problem. So if you study the same problem, let's say you put a boundary condition and initial data, and you put the parabolic problem, Bars, Poreta, and Chamba in 2010 prove further properties of the ergodic problem. The ergodic problem is a sort of eigenvalue problem, has a non-degeneracy, because if you put a constant, you have a solution. They prove some characterization of the eigenvalue problem, and what they prove is that if the ergodic constant is negative, then the stationary problem has a solution. So the problem without UT here has a solution without initial condition, of course, and the parabolic problem converges to the solution. So that's what they prove. And what happens if the stationary problem has no solution? Then they prove that this is the characterization they have. They prove that the ergodic constant must be positive when the stationary problem doesn't have a solution. So, and they establish some what happened in all cases, but here I want to mention just one case. For example, if C0 is positive and P is in between 2 and 3/3, then they prove that the parabolic constant plus this C0t converge actually to the ergodic problem as t goes to infinity. Local uniform for some constant mu. This is a constant because the problem has some this constant invariant. And they also prove other asymptotic in the case C0 and P between 1 and 1/3, which are more less complicated, but at the end they cannot avoid that solution goes all the way to minus infinity. This happens when C is 0 somehow. And this is why the result is hard to explain here, and it's not my object of the talk. I just wanted here to mention that I with Bars also and Rodriguez, a PhD student, an old PhD student, which is we have this type of results, so convergence to the ergodic problem in Rn, for very general initial condition and very unbounded. That's the point here. Very general and unbounded initial condition and F. So convergent to the in all cases for P bigger than 1, even bigger than bigger than 2 also. So, and it converges to what is called an ergodic pair, which is, well, it's a pair because it's somehow the eigenvalue, a sort of eigenvalue, and the function. This is called what ergodic pair. So I come back to the non-local case and explain my result. So before, maybe I just mentioned that there are large solutions in the non-local setting studied before by myself and Chen and Felmer in 2015, which is close to our approach here, because what we use is Perron method, a version of Perron method to find explosive solution. And here this in another word by Dendello. They have many other words maybe after that, but here just for equation of this type, not depending on the gradient. This is the point here, because my equation depends on my equation, the equation I studied depend on the gradient, but here without the gradient, Dendello also proved using the properties of the green function in 2 works or even more, existence of a large solution. So now I come back to my main result in the model case. So the model case, because I can even put more general operator, but let's stay in the model case. So really focus on this equation. So I need to to studying this equation, I need to find some critical values. There are 3 critical exponents that will appear, which are very easy. One is P1, which is S plus 1/2, P2, which is S plus 1 divided by 2 minus S, and P0, which is 2S over 2 minus S. So the exponent have some properties like P1 is less than P2, P less than 2PS, and so on. It's always better to write a picture, right? So I put a picture here, which is nice. So you have here in this axis, you have S, and here you have P. So you have P0, which is not that relevant in that problem, but anyway, I will explain in my theorem what's the role of P0. So you have P0, then P1, and then P2. And the last is the red one, which is the upper bound for my P that I can consider given a S, so it's 2S. So this is the picture of my theorem at the end. And there is a special number here, which is S star, which is this number where these two curves cross. But it's not that relevant at the end. I will explain it in a minute. So what the theorem says, it's very different of the Lasry-Lions type result. And what they says is the following. So here's my theorem. I will just put for simplicity lambda bigger than. So the ergodic problem here is not that clear what is happened. So I just, in the model case, I will put lambda bigger than 0. And I will put S between 1/2 and 1, and P here. And if P is between 1 and 2S, I will define this number, 2S, which is more or less the same except scaling of the Lasry-Lions type solution. So we have 3 types of solution. And one is the one parameter family of solution, which is close to S harmonic function, unbounded S harmonic function. So if P is less than P2, P2 is somehow a barrier between the existence of this. So if I go back here to the picture here, below this purple line, you have a family of S harmonic function. What is this? Even they goes to plus infinity or minus infinity, because you have for all t not trivial a solution which behave like 1 minus s at the boundary, or its explosion like s minus 1. So this really happened. And here, and you have a error depending on p. And what happened below P0 is that this gamma here is not singular. So really you have a precise, it's like really a harmonic function. But it's for the for this problem, for star, right? So with the gradient. So somehow below the yellow one, you have really up to 0, let's say, you have really harmonic things. So the gradient doesn't affect too much the equation. You have really harmonic things. And and here in between the yellow and the purple, you have other type of things here, which is somehow you have the harmonic, but the perturbation is still singular. Yeah. So, but anyway. So this is the first solution I get, and you have some order. So you have T1. If T1 is less than T1, the solution are really ordered. So here now is what happened with if P is in between P1 and P2. Here we find really the Lasry-Lions type solution. This is the Lasry-Lions type solution. So you have the power here, which is this power, replacing what, but it's the same feature. So really you have a solution that's behaved like this power at the boundary. Here, this power is positive, so because beta is negative, and so it's behaved singular with a t, which is the scaling somehow. So it's really the positive scale. So and this is between P1 and P2. And the last solution, which is never present, this is the only solution. This is the only solution. The 2 case is the only solution in Lasry-Lions type problem. But here we have also a negative scale solution, which is the negative scale solution is a solution that goes to minus infinity at the boundary. So this goes to plus infinity, this goes to minus infinity, but you need to be P needs to be bigger than P2 and small than 2s. So roughly speaking, or what the theorem says, between the green line and P2, you have the Lasry-Lions type solution. And this restriction is not, P1 is not present in the local case. So, but here we have this restriction because it's related with a L1 bound. I will remark that. But here we have coexistence of the harmonic, let's say, and the other one. And between the purple and the red line, you have the negative scale. Here you have a negative scale and positive scale. And yeah, we have somehow coexistence of all the family. In between P2, all the family, because it can be T can be positive or negative. We have the scale solution and we have the negative scale solution. So these are the 3 types of solution, and we have coexistence of this in between these 2 lines. Now, of course, here in between these 2 lines, we have coexistence of these 2 family of solution. And the remark is that we have non-uniqueness. Of course, we have a family, even a family, but even non-uniqueness because the solution in case 2 is bigger, even bigger than the solution of UT. And what I mentioned, the condition P bigger than P1 for the case 2 solution is that we need so that the integral operator is well defined, that the solution is in L1. So some extension, very rough. I can put a fully nonlinear operator with kernel comparable to the Laplacian, and study the same problem with even with a white, a Dirichlet condition outside with a L1 with a white, so that the operator is well defined. But here I want to mention that we can even go with lambda negative. Somehow, if you split the operator in so lambda can be even negative. Why? Because somehow if you split the operator in the censored one, so it jumps inside and outside, you win coercivity. Still the censored operator is elliptic, so you win coercivity. So it's not clear what is the ergodic problem here. Yes, I wanted to mention. And you can solve for the model case even with lambda bigger than this number, which is the infimum of somehow the kernel outside with the point inside. Yeah, so it's really this. What's behind of the result? Well, I want to explain a little what's behind. The one-dimensional case, of course, that's behind. And that's the key of the proof. And what's the key of the proof? It's that for the fractional Laplacian in the line, in the half line, you have that the fractional Laplacian is minus a function times it derivative is 2s, the operator. But you have that it's a convex function, so s is harmonic, s minus 1 is harmonic, and you have a c which is convex and looks like this, right? And what is then in the local case? Of course, if you derive twice a power, you have this polynomial. So this point goes to 0, and this. So here you have a different feature, because somehow in the one-dimensional case you have this here. This region is related with the Lasry-Lions type solution. This 0 here is the family 1 solution. The 0 here, because we look at negative power, so because it's singular. But and here is the negative scale. This part is negative scale. Here the family 1 scale. This is roughly speaking, of course, and this is the Lasry-Lions type. Of course, Lasry-Lions type, if you consider really this quadratic function which has 0 at 0 and 0 at 1, of course, it's not unbounded here, but this is just positive for negative power. Here we have all a region where you have negative and a 0 there. So this is really the main things around. And of course, we need to do this and reduce in a regular domain the thing. And this is the key lemma. And the key lemma says if you have a regular domain, and you put the distance, what you have is really you have that it's behaved like the distance to tau minus distance to tau, or tau is between -1 and 2s, and it's really behaved like the one-dimensional plus, because here is the one-dimensional thing, plus a error term. So this is the expansion we have close to the boundary, and with that, and here is the one-dimensional thing. The CT is the tau is the one-dimensional thing, which is this picture that I mentioned, which is related to that, and it's exactly that, and has these properties that I mentioned before. So it's a picture. So it goes to plus infinity there, plus infinity there, and it has 2, 0, and it's positive, and then it's negative in the other side. So it's really this picture, and that's behind. And so, roughly speaking, here you have in this region you have the negative scale. Here you have the positive scale, and here you have the family 1 scale. And this is the proof at the end. But of course, this is the lemma, because for that lemma you need to rectify or blow up the boundary and really reduced to the one-dimensional thing. And then, of course, here I mentioned, for example, this condition, you have C beta positive, and then you can construct sub and super solution of Lasry-Lions type and apply Perron method, extension of Perron method that applies to this unbounded problem. So that's what I want to talk. Thank you.
Thank you. Okay, we have 3 minutes for questions. Yes, okay.
Thank you, Vanya Wagner. Thank you for the lovely presentation. I have actually 2 relatively short questions. So the first one is regarding the extensions of the operators. You mentioned you can extend these results for more general integral operators where the kernel is somehow comparable to the fractional Laplacian one. Yes. What about more general kernels? I see that maybe because of this lemma, which requires some exact results. Yeah.
I'm finished this paper. I'm writing this, but what happened with more general operator? It's my impression. I didn't make the exact computation. Is this S-1 on S move to some still S depending on the operator. It's not really S. It's some, let's say, beta 1, beta 2, 2 numbers that are not really like this, are changed, but you have the same feature. And so the theorems became more complicated because S is not anymore, or you don't have this precise number. So you have a generalization, but these numbers are not S-1 nor S. So you have a more general, a number that you don't know what it is. You cannot compute it like this one-dimensional thing, because you have some maybe lambdas of the ellipticity going around, and this number change with the ellipticities, let's say.
Yeah. So this is maybe also a comment. So you can get some type of upper bound for this idea in the proof, but the lower bound is the issue. And then I guess this Perron method fails because you don't get the subsolution of the same order. But
yeah, roughly speaking, yes. Okay. Yes.
And the other question was regarding the explosion rate at the boundary of your solution. So the type 2 and 3 solutions, where you have the explosion rate of delta 2, distance to the boundary to the power beta.
Yes.
So your result says that there exists a family of solutions with this explosion rate. But what about solutions?
No.
Sorry.
Yeah. The family is just with the harmonic, let's say harmonic, because it behaves like S-1.
Okay, this is the
family, and this is there exists a constant. So it's only one constant, a precise constant, more or less. Okay. The operator and the gradient is the same. This is the unique, is the same order, let's say. The gradient and the operator is the same order, and you fix the constant. So really the constant is so that they both are exactly the same. So the constant is fixed, really fixed.
Okay, so you don't.
This is the Lasry-Lions. The positive one is the Lasry-Lions scale solution. So really a fixed T. Not
okay. So we cannot investigate solutions of this different explosion rate. This is the explosion rate.
Exactly.
Okay, thank you so much.
But we didn't prove uniqueness, so it's open. If in uniqueness fail in general because we have coexistence of the family 1 and family 2, but maybe uniqueness in that class is open because you don't know if there are other solutions that explode at that rate. It's just we prove the existence. It's not proof that it's unique in that rate. It's not unique in general, but in that rate, it's not. I don't know if it's unique or not.
Any further questions? Okay, thank you, Alexander.